So it starts at PDF page 55. There's a kestrel flying through the air. So basically, kinematics means how things move, as opposed to dynamics, which is sort of why things move. And by one-dimensional motion, we're just talking about motion along a straight line, meaning that it doesn't turn. So it turns out you can move along a straight line or a curvy line. And these are two very different things in physics. So we're going to start with moving along a line and no turning. And then for two-dimensional motion in the next chapter, we'll talk about what happens when you're actually turning, two or three-dimensional motion. Definitions to go through. Position. So if you have, for example, a coordinate system with an x-axis and an origin, then your position on the x-axis is a number, which could be positive or negative, depending if you're one side of the origin or the opposite side of the origin. So that's position. Displacement means the change in position. Typically, it's going to happen over some time. And the equation here that's important is delta x equals xf minus x0. So xf and x0, those are the final and initial positions. So these little subscripts refer to final, and 0 just refers to initial. It means like the zero time position. So final minus initial gives you this triangle is called delta, so it means the change in x, delta x. That's displacement. So for example, if someone starts at 1.5 meters and goes to 3.5, the displacement is 3.5 minus 1.5 is plus 2 meters. If somebody along their x-axis starts at 6 meters, but then travels backwards to 2 meters, then the final is actually less than the initial. You get 2 minus 6, you get negative 4 is your displacement in that case. So distance is the okay, this is a bit of a weird thing. First they say distance is defined to be the magnitude of the displacement, and then they say that it's not. It's important that the distance is not the magnitude of the So I think what they mean here is when they say distance traveled, that's what I tend to mean when I say distance. Distance traveled is not the same as the magnitude of the displacement. And the example here is that a cyclist rides 3 kilometers west, then turns around, does a U-turn and rides 2 kilometers east. Question A, what is their displacement? And question B, what distance do they ride? So the first thing they do is define plus x to be in the east direction and minus x to be in the west direction, which is fine. You can define that any way you want, but once you do that, then you know that the initial delta x is negative because you're going west, minus 3 kilometers, and then the second 2 kilometers to the east is plus 2 kilometers. So when you add the two displacements, you get negative 1 kilometer. So they end up 1 kilometer to the west of where they started. So that's the displacement. The question is, what's the distance? Well, the distance they traveled is actually 5 kilometers because first you rode 3 and then you rode 2. It doesn't matter what direction. If you had an odometer on your bike showing how far you went, it would be 5 kilometers. So the magnitude of the displacement is just the absolute value of negative 1, which is 1, but the distance traveled is 5. And then say section 2.2 is about vectors, scalars, and coordinate systems. This is about using this plus or minus to indicate direction in one dimension. So there's sort of a difference. We'll talk about this a lot more when we get into chapter 3, but we say that a scalar is a quantity that has like a magnitude, a size, but no direction. And that's typically what you type in a calculator. But I guess if you think of temperature, for example, or mass, these are scalar quantities. Even though temperature can actually go zero, go negative. There's a zero temperature on the Celsius scale anyways, and it allows you to go to negative. The negative doesn't tell you about direction there. It just tells you, again, about this temperature. So okay, and then a vector is something that has a direction, such as displacement, for example, is a vector. You're going east or you're going west. And so you need a coordinate system to give you whether plus or minus tells you one direction or another. That's what that's all about. Sometimes we go to the right is plus, to the left is minus, up is often plus. Down is often minus, but you can define these any way you want in order to solve the problem you've got. Section 2.3 is called time, velocity, and speed. Basic idea, time it's a scalar quantity which increases with time. I don't know, it's just the reading on, for example, a watch or a stopwatch or something, and we measure it in seconds. So an elapsed time, I guess, is the difference between the final time and the initial time. So you could say that something takes, I guess if the lecture starts at 11 a.m. and ends at, actually if it starts at 11:10 a.m. like my lectures do and ends at noon, then the elapsed time's 50 minutes is your delta t there. So, okay. And then there's the whole velocity versus speed debacle. So the idea, and there's also average velocity versus instantaneous velocity. Okay, so let's go through these in the order of the book. Average velocity is defined as the displacement divided by the elapsed time. So it's delta x over delta t, or x final minus x initial, divided by t final minus t initial. So since displacement is a vector, it has a direction, the average velocity is also a vector. It has a direction as well. And there's some examples of that. If you go backwards minus 4 meters in the negative x direction, then and it takes you 5 seconds, then your average velocity is negative 0.8 meters per second. So the units here come from the units of the displacement divided by the units of time. So if you measure displacement meters, time in seconds, then you say that your average velocity is in meters per second. Okay, then there's something called instantaneous velocity. Instantaneous velocity is like, it is the average velocity, but only measured over a very, very, very small time interval. So you allow the time interval to get very short. So the denominator is a very small number. Also the numerator, the displacement, is a very small number. But when you divide those, there's a limit where it's your velocity at that moment, your instantaneous velocity. And that's also a vector because it has direction. But speed in physics means the magnitude of the velocity. So speed is always positive, and it just means without the direction how fast you're going. So if your velocity is negative 3 meters per second, your speed is 3 meters per second. If your velocity is 40 kilometers per hour, your speed is 40 kilometers per hour. Okay, you just take off a minus sign if there is one. And lastly, this chapter includes some graphs. So there's something called a position time graph. This is showing your position along perhaps the x-axis. You put that on the vertical axis, and then on the horizontal axis you put time, in this case in hours. And then it turns out that the slope of a position versus time graph down here, you take the slope of this, rise over run kind of thing, is equal to the velocity. Actually, the instantaneous velocity. So all along here, there's a constant slope. The rise is 3 kilometers. The run looks to be about 0.25 hours. So 3 divided by 0.25, I think, equals plus 12. So there's a plus 12 kilometers per hour until suddenly the velocity changes at this moment, and then you've got the rise is now negative 3, and the run is again 0.25, so you get negative 12 kilometers per hour. So that's the velocity. You can now make a graph of velocity versus time. Constant velocity of plus 12 switches to minus 12. And then if you want, you can take the absolute value of the velocity to get the speed. The speed is the same no matter which direction you're going in this particular case. You're going one way, flip it around, go the other way at the same speed. So you just see 12 the entire time. 2.4 on acceleration, and it shows a plane here which is slowing down. Its acceleration is opposite in direction to its velocity. So there's a definition of average acceleration. You can see here it's the change in velocity divided by the change in time, or Vf minus V0 divided by Tf minus T0. So this looks very similar to the definition of velocity, which was the change in position per time. And that was meters per second. So this is actually meters per second on the top, per second on the bottom, so you get meters per second squared. So basically, I actually think acceleration is one of the most difficult concepts in this course, and it's also one of the most foundational and important concepts in physics. You can't understand Newton's second law without first understanding acceleration. Newton's second law being that you can find acceleration as being the net force on an object divided by its mass. So you need to know what acceleration is, and if you think it's similar to velocity, you couldn't be more wrong. So for example, what's velocity? It's the rate of change of position. So, and acceleration is the rate of change of velocity. So I would say that acceleration is as different from velocity as velocity is different than position. Okay, you wouldn't confuse where you are with how fast you're going. Well, you shouldn't confuse how fast you're accelerating or what's your magnitude of your acceleration with your speed. Okay, those are not the same thing. So again, the videos, watching these pre-class videos is not a substitute for doing the reading, and this is very, very important today. I really encourage you to read this section, misconception alert, deceleration versus negative acceleration. That's important. This all depends on which way you define plus. Okay, something can be decelerating and have positive acceleration, and these are some different examples of acceleration in various different directions and velocity in different directions. But basic idea is that if the velocity vector and the acceleration vector are in the same direction, it means your object is speeding up. If the velocity vector and the acceleration vector are in opposite directions, it means it's slowing down. Just as there was instantaneous velocity as opposed to average velocity, there's also instantaneous acceleration. It just means it's that average acceleration, but over a very small delta t. Okay, so it turns out to be the acceleration at a specific instant of time. And you can graph instantaneous acceleration versus time. There's some important unit conversions. Delta V here is 30 kilometers per hour over 20 seconds. You're going to have to convert kilometers to meters and hours to seconds to get meters and seconds. You're trying to get all the units of distance in meters and all the units of time in seconds to calculate things, and they're called SI units, the System International. And so now for something where the velocity is changing, you've got position versus time. The slope of the position versus time graph becomes your instantaneous velocity versus time. And similarly, the slope of the velocity versus time graph becomes your instantaneous acceleration versus time. So positive slope here, then velocity remains constant, that's zero acceleration. And then when velocity is decreasing, you get a negative acceleration. So I'm going to let you read through all of that. Pretty important. And it ends, of course, with the PhET Explorations Moving Man Simulation. You can click on this, taking you off to this University of Colorado Boulder animation. I really encourage you to try this one out. I would just run the Chirp compatible version. So this is the PhET Moving Man Simulation. Basically, if you give this guy a velocity of +4, for example, then he moves along. And you can see graphs of his position versus time. Here's 6 seconds. So during the first 2 seconds, his position goes up. You can see it's 1.5 meters in 1.2 seconds. 5 divided by 1.2 is 4 meters per second. And here his acceleration is 0. So let's restart this guy at position of 0. We'll give him an initial velocity of 4. Let's put to 0 actually, and put his acceleration to +1. Start him off, and he speeds up, speeds up, speeds up, speeds up. Oop, and he hits the wall. So what you see here is now his velocity goes up by 1 meter per second every second. So after 1 second, he's going 1 meter per second. After 4 seconds, he's going 4 meters per second. And his position goes up as a curved parabolic line. Let's start him again at 0 position. Let's give him a positive velocity of 4 meters per second and a negative acceleration of 1 meter per second. So he's slowing down. At first, he slows down, reaches a maximum position, then he's speeding up, but going to the left. So let's stop him at 8 seconds and take a look at the graphs. You can see the velocity starts at +4. And let's zoom in on the acceleration. The acceleration is a constant value of -1. So for every second, he loses 1 meter per second of velocity. It goes through 0. This is the turning point when he turns around at the house. And that happens when he's the farthest to the right that he can possibly get. That's about 8 meters. Then it turns around. So once again, this is a parabolic position versus time graph, and his velocity is a straight line with a negative slope. You can sort of see here. It starts off with a positive velocity, goes through 0, then it's a negative velocity as he's moving to the left. So he's slowing down, then he stops, and then he's speeding up. We're in section 2.5 on paper page 58 and the PDF page 76. This section is called Motion Equations for Constant Acceleration in One Dimension. We should start with notation T, X, V, and A. So first, let us make some simplifications in notation. Delta T is T final minus T initial, but T initial, we can usually set that to be 0. That's sort of the definition of initial time, is when T equals 0. So delta T equals T final, and we're just going to call that T, the time. Delta X is X final minus X initial. Delta V, change in velocity, is V minus the initial V. So 0 denotes an initial value, and the absence of subscript denotes the final value in whatever motion is under consideration. And at the top of the next page, we have this notation A for acceleration. So the assumption of this section is that acceleration is constant. And I just want to remind you that there are lots of examples of motion which acceleration is not constant. When you think about the moving man FET animation from last class, you could see that there was a graph of acceleration versus time, and it went all over the place. And there's a lot of examples of that. So when is acceleration constant? Well, one good example is falling. Or what we call a free fall. If something has only one force on it, and that's the force of gravity, then it's going to have a constant acceleration downwards of 9.8 meters per second squared. And there are other examples where acceleration can be constant. So if that is the case, then the average acceleration is equal to the instantaneous acceleration because they're constant. And in that case, we can derive these equations of constant acceleration. So I think we're going to go to the whiteboard to actually derive these equations rather than go through the textbook. So I'm going to call this the equations of constant acceleration. And by definition, the average velocity, which is V with a little line on top, meaning the average, is equal to the change in position divided by the change in time. And with that notation we talked about before, that's going to be X minus X initial divided by the time. And what we can do is rearrange that, multiply the left and right hand sides by T, and you get V average times T is equal to X minus X0. And then you can add X0 to both sides, flip it, the X to the other side, and you get X equals X0 plus V with the bar on top times T. And your book calls that one equation 2.50. And the next thing is just this sort of obvious idea, which is that the average velocity, that I guess if acceleration is constant, then the average velocity is the final velocity plus the initial velocity divided by 2. It's halfway between the initial and final. And your book calls this one equation 2.51. But what I'm going to do is combine these two equations. I'm just going to plug this into here. Combination equations 2.50 and 2.51. It's a combination equation 2.50, 2.51. Is going to be X is equal to the initial X plus V0 divided by 2 all times T. And I'll call that equation, 2.51 B or something like that. So that's a good one to know. First equation of 4. Second equation is from definition of acceleration. well, actually this is the definition of average acceleration, but that's the same as acceleration if a is constant, is just delta v divided by delta t. So again, with our definitions, that's v minus v initial all divided by the time. And so you can rearrange that. You get a times t is equal to v minus v0. So v is equal to v0 plus a t. So I'm going to call that equation 2.52. And the next thing I'm going to do, which is going to look a little weird, is I'm going to take this equation. I'm going to add v0 to both sides. So v plus v0 is equal to 2v0 plus a times t. And then I'm going to divide both sides by 2. V plus v0 over 2 is equal to, this divided by 2 is just back to v0 plus 1/2 times a times t. Remember, this is just average velocity. So this is average velocity is equal to v0 plus 1/2 a t. And if you go back to equation 2.50, remember that x is equal to x0 plus the average velocity times t. So I can take this and just plug it in to right there. And I get that x is equal to x0 plus, and all this stuff. So v0 plus 1/2 a times t, all times t. And now I can take that t and multiply it in, and I get x is equal to x0 plus v0 times t plus 1/2 a t squared. And this is called equation 2.53. So the last thing is that if we take equation 2.52, which remember was v is equal to v0 plus at, and we solve this for t, we get that v minus v0 is equal to a times t. Divide both sides by a, and we get that t is equal to v minus v0 divided by a. And of course we also have that v average is equal to v plus v0 all divided by 2. And again, let's go back to equation 2.50, which is that x is equal to x0 plus the average speed times the time. So what I'm going to do, it's a little kind of complicated, but I'm going to take this average v, I'm going to plug it into there, and then take this t, and I'm going to plug it into there. And so I can write out x is equal to x0 plus v plus v0 all divided by 2 times v minus v0 all divided by a. And so, I don't know if you remember your algebra, x is equal to x0 plus 2a is on the bottom, and we've got v plus v0 times v minus v0. So when you take a plus b multiplied by a minus b, and to put a squared minus b squared. So x is equal to x0 plus v squared minus v0 squared all over 2a. Actually solve this for the final velocity squared. So first thing I'll do is I'll subtract x0 from both sides, and I've got v squared minus v0 squared all over 2a. Now I'm going to multiply both sides by 2a, so I'll get 2a times x minus x0 is equal to v squared minus v initial squared, and then I'll add v initial squared to both sides, flip it around, and I get v squared is equal to v initial squared plus 2 times a times x minus x initial. And this one is the last of our 4 equations, and this is called equation 2.54. And here they are. So the textbook lists these as 5 equations, but I have combined the first 2 with the v average to be just one equation, x equals x sub 0 plus this average speed times t. So if the acceleration is constant, then you can find x this way, and then there's the other 3 equations here. So I would like you to go through this chapter, try the examples, this section. it's always good to read the book, but now you've seen those equations derived. And the last section for today is this problem-solving basics. And it's talking about problem-solving steps. There's no simple step-by-step method that works for every problem. The following general procedures facilitate problem solving. I think this is really, really useful. So I've taken these 6 steps and put them in a Prezi presentation. So here's College Physics' problem-solving basics for one-dimensional kinematics. It's 6 steps, which we'll start with. Step number 1 is draw a diagram. Draw a diagram, draw a diagram. I'm sorry to repeat myself, but it'll help you remember. Step number 1 is draw a diagram. Draw a diagram, draw a diagram.
Wow, that does work.
Drawing a simple sketch or diagram will help you think about which physics principles are involved. Once you've identified the physics principles, it's much easier to find and apply the equations to represent the laws and quantities. Don't forget to define your axis, or axes if it's two-dimensional. You should decide which direction is positive and note that on your diagram. And making decisions like this and sticking to them is part of how you solve problems. And if you get into trouble, you can always go back and start again and try a different decision. Step 2, make a list of knowns. Make a list of numbers that were given in the problem as stated. And you can add this right next to your sketch. For example, if it says somewhere that the initial velocity is 5 meters per second to the right, and on your diagram you identified pluses to the right, then you could write down v sub 0 equals plus 5 meters per second. And you can choose the notation. So you could, if you wanted, you could put VI instead of V0, and don't forget the units. Some numbers are inferred rather than explicitly stated. So it might say that something is stopped, or it might release from rest is another good one. It means that the initial velocity is 0. And sometimes we can define initial time as 0 or initial position as 0. So you can write those down as your knowns. Also make a list of what's called unknowns or unknowns. So in particular, what exactly needs to be determined in the problem to get the answer and to move on. Some unknowns you don't actually care about, so there's no real need to list them unless they're somehow important in determining the answer. So keep your eye on the goal here. And you might notice that you're going to use a lot of paper. I actually have a whole recycling bin, and I'll go in and use the blank sides of old paper. I find, for me, physics problem solving requires writing a lot. Step 4, find the equation or equations that can help you solve the problem. So your list of knowns and unknowns can help. It's easiest if you can find equations that only have one unknown. If you have 2 unknowns, you're going to use 2 independent equations and combine them. You could solve for both. 3 unknowns requires 3 equations, etc. This is the tricky part, this step 4, okay? It takes some practice, and it's good to remind yourself of the physics principles during this part. The equations all mean something, and you are using them for a reason. Sometimes thinking about the reasons behind the equations helps you figure out which ones to use. There may be multiple steps if the problem is involved. Sometimes you have to first solve for one thing and then use that answer to solve for something else. So, and I'd recommend if you do this, keep things in symbolic form at this point. Don't plug in the numbers until the last second. So, and sometimes you find that one of your unknowns will cancel out and you don't have to worry about it, and that saves time. But basically, don't give up. You can do it. keep on going. To step 5. So step 5 is substitute the knowns into the appropriate equation or equations and solve for the numerical answer. This is sort of the last step. It's one of the easier parts. As long as you're careful of typing numbers into your calculator, it's not real tricky. You just do it. Don't forget, you do need a calculator for the term tests and the final exam. So I would get one now. Use it for your problem sets. Don't use your phone or Excel or something for problem sets, because you sure won't be allowed to have your phone during the tests and the exam. Also, on these steps 4 and 5, don't forget units. Your final answer will require units, and all of your knowns have units as well. So it can be a good idea to write down the units at every step. The units actually cancel just like, or multiply times each other just like other things. just like variables. So this can be a good way to check your answer, which leads us to step 6, the sanity check. Does your answer make sense? For example, if you've been asked to calculate a distance it takes a plane to stop on the runway, and your answer is 0.0053 millimeters, okay, that clearly is something wrong. So take a look at your answer, think about what's going on and what the physics is, and decide if it seems okay. And if it doesn't, you can look back for mistakes in the first 5 steps. And here's the last step is just do a units check. Look at the units. If you've been careful about keeping track of your units in the previous couple of steps, then they should match up here. You should get, meters per second if it's velocity, or meters if it's distance, etc.
My name's Bob Harlow. I'm Professor Jason Harlow's identical twin brother. This is the physics building. Today, I'm going to talk to you about falling objects.
Unfortunately, that was the last known footage of my dear old brother Bob. But don't worry, I'm here and I can teach you today about falling objects. So this is section 2.7 on page 89 of your PDF, or 71 paper version. And this is about gravity. The most remarkable and unexpected fact about falling objects is that if air resistance and friction are negligible, then all objects fall towards the center of the Earth with the same constant acceleration, independent of their mass. This experimentally determined fact is unexpected because we are so accustomed to the effects of air resistance and friction that we expect lighter objects to fall slower than heavier ones. Here they show an experiment that was done on the moon where an astronaut dropped a hammer and a feather at the same time, and they fell with the same acceleration. And the reason they fall with the same acceleration is because they are in a vacuum, meaning that there's no air resistance that slows down the feather. So air resistance acting on a hammer is pretty low here on Earth, but it's a lot compared to the weight of a feather, and so feathers don't fall at this regular rate. But they would if you took away all the air. So here on Earth, the acceleration due to gravity for objects that are not affected much by air resistance is 9.80 meters per second squared. So if it was a vacuum, everything would fall at this rate. But if there is air, then really heavy or very condensed objects will fall with approximately with this rate, maybe a little less. So once you know that, there are these same kinematics equations, which are the equations of constant acceleration, at least 3 of them, but they've rewritten them here with, instead of x, they've written y. Okay, so y here, I guess would mean vertically up. So plus y is in the up direction. Then the acceleration in that direction is negative g. So instead of a, like plus 1/2 at squared, you put in minus 1/2 gt squared. And then this is the y component of the velocity, and speed squared there. So those are handy equations. There's a couple of good examples. Here's a rock thrown upward. So I encourage you to work through that example. Another example of a rock that is thrown downward, so you can have a negative initial velocity and a negative acceleration. And here's an example I want to pause on, example 2.16, finding g from data on a falling object, because this kind of shows really what happens here. So here is a rock, metal ball, which has very negligible air resistance on it, and is released from rest, meaning that someone lets it go without throwing it up or throwing it down, but just releases it gently from rest. So, and you can define, I guess, your initial y position as being 0. So in that case, initial time is 0, initial y is 0, and if it's released from rest, the initial v, or velocity, is 0. So then, 0.1 seconds later, for every 0.1 seconds, the velocity changes. There's a delta v of negative 0.98, because that's 9.8 meters per second squared times 0.1 seconds. You get negative 0.98 meters per second. So, and that just keeps on happening. Every tick of the clock of 0.1 seconds gives it an additional delta v of negative 9.98, so almost 1, right? So or almost 0.1. So, sorry, almost 1. So -1, -2, -3, -4, -5 meters per second. So that's the speed, but the distance between these positions, if you were to take like a snapshot at individual moments, that increases. So originally, the sort of average speed is less than 0.1, so it only goes a tiny little bit. But as the average speed between moments gets bigger, the distance gets bigger and bigger. And so if you were to graph that, you actually get a curved graph of position position on the vertical axis here downwards versus time for the falling sphere. But you get a straight line for velocity versus time. And you just get no line at all, just a negative 9.8 constant for acceleration versus time. And that leads us to section 2.8, graphical analysis of one-dimensional motion. I encourage you to look at this PhET exploration. So if we click on that, it takes us to this equation grapher. So basically you can select the different constants in this equation. Y is the vertical axis equals ax squared plus bx plus c. This is called the quadratic equation because it's got these x to the power of 2 as the largest factor of x. So c is just the constant. If a and b are 0, then this just brings it up and down. B is the slope. So actually c is sometimes called the y-intercept because it turns out to be the position, the y position at x equals 0. And then a is that quadratic term. So this is what gives it its curviness. So sometimes, I don't know, you could look at something that was thrown with an initial position of 3.6. Let's say y here is, I don't know, vertical position, and x is now time. If you make x time, then something that's thrown with an initial position of 3.6 upwards with 1.4 meters per second, and then accelerates downwards. Oh, I can't get to negative 9.8 on this thing, but you get it. It would be, it would look something like that. It would go up and down a curved path. So you can play with that. So the basic idea here, so again, the equation of a straight line is sometimes y equals mx plus b, where m is the slope and b is the y-intercept. We're going to kind of apply that equation to our equations of constant acceleration. So the first one we had was x equals x0 plus vt, or v average times t. So that actually is that equation. It's just that instead of y, now we have x, and instead of x, we have t. And instead of slope, we have that average velocity, and instead of the y-intercept, which is, I guess, the x-intercept, you have the initial position. And then there's graphs of motion when a is constant, but a does not equal 0. These are these curved lines. You can actually make a plot of v versus time, and here is that equation. It's another one of our equations of constant acceleration. V equals v sub 0 plus a times t. So in this case, you've got v on the vertical axis and t on the x-axis, and a, the acceleration, is the slope, and the initial speed is your y-intercept there. So if you had a graph of velocity versus time, you could get the acceleration just by dividing delta v divided by delta t, so rise over run there. And that's it for chapter 2. Actually, there's a glossary with some good terms. There's a summary which goes on to a couple of pages of every section, including falling objects and graphical analysis. And then there are a bunch of conceptual questions followed by problems.